All right, so we are going to do a quick review of limits and continuity. So what is a limit? A limit is the y value that a function approaches from both the left and the right side of a given x value. So a limit is the y value. Okay, so we're going to look at these quick functions. First, the function at f of -3. So we're going to look at each one of those. So when the x value is -3, the y value is 4. And in this case, the limit as x approaches -3, as we look both from the left and from the right, that y value is 4. In the second one, f of -3 doesn't exist. There's a hole there, which we can say DNE for does not exist. But the limit, as we look from the left and from the right, what's happening around that point is still the same. So the limit as x approaches -3 is still 4. Here the function as the function of -3 is where there is a closed point, so that is the y value of 1. And still, even though the function at -3 is 1, what's happening around -3 still gives us the limit of 4. In this fourth one, though, the function at -3 is, again, where the function is closed, not where there's a hole. So that function at -3 would be 1. But the limit here, we say, does not exist. As we look at the function coming from the left, we get the y value of 4, and coming from the right, we get the y value of 1. Since those are not the same, we say the limit doesn't exist. We'll talk about that more in a second. And in this last one, the closed point, f of -3 is equal to 2. And the limit as x approaches -3, again, is 4 from the left and 1 from the right, which is not the same value. So we say that the limit does not exist. So this one-sided limit is what's happening when we're looking from one direction or the other. So a one-sided limit is the y value a function approaches as you approach a given x value from either the left or right side. So an overall limit is looking from both directions. A one-sided limit is looking from one or the other. So in this picture here, we would say the limit of f as x approaches 3 from the left side is -1. So this little negative symbol notates that we're coming from the left, and that y value is -1, which is how we get a y value, a limit from the left of -1. And the limit of f as x approaches 3 from the right side, which we notate with this little plus symbol, is 2. So those two numbers are the one-sided limits. But in order for an overall limit to exist, the limit from the left must be equal to the limit from the right. So in this picture above, we would say that the limit does not exist, which again we can notate with that DNE. All right, so let's look at a few different examples. In letter A, the limit as x approaches -2 from the left means we're looking at the x value of -2, and we're looking as the function approaches from the left-hand side, that y value is 1. Versus in B, the limit as x approaches -2 from the right means we're coming from the right-hand side, and that y value is -2. C is the limit as x approaches -2, the overall limit, right? There's no plus or minus there, so that means we're talking about the overall limit as x approaches -2. Since A and B, the left and the right, are not the same number, that means the limit as x approaches -2 does not exist. And now we're going to switch x values, so I'm going to change that. In D, the limit as x approaches 1. So here's our x value of 1. The limit as x approaches 1 from the left is the same as from the right. We don't care about whether there's a hole or not. We just care about what's happening around it, and that's approaching the y value of 1. So that means the limit is 1. In E, the limit as x approaches 0 means we're looking at the y value of 0. And again, we're looking at what's happening from the left and what's happening from the right. That's approaching the y value of -2. In F, as x approaches 3 from the left, so here's our x value of 3, and we're not talking about the overall limit, we just care about what's happening from the left-hand side. It happens to be the same as what's happening from the left, or from the right, but we only care about the left. So the limit as x approaches 3 from the left is the y value of 5. In G, as the limit as x approaches -1, here's -1. Overall limit means we care about the left and the right. That y value is -3. H, the limit as x approaches -3. Here's my x value of -3 from the left, and from the right, it's approaching the y value of 0. And now f of -2 means I care about the actual function at -2, not the limit. I care where there's a closed point. In this case, it is at 1. And in J, f of 1, again, means I don't care about the limit. I care about where there's a closed function. So in this case, f of 1 is -2. All right, so then we're going to sketch a graph of a function that satisfies all of these different conditions. F of 1 is equal to 2, so I'm going to go to the x value of 1, and I know that there's going to be a closed dot at 2. The limit as x approaches 1 from the left is equal to 4, so I'm going to go to the x value of 1 and the y value of 4, and I know that's going to be open because I already have a closed point at 1. And I know that we're talking about what's happening as I come from the left, and I'm going to come back to that in a second. And the limit as x approaches 1 from the right is -3, so I'm going to go down to the y value of -3. Again, that has to be an open dot because we already have a closed dot at 1. We already know what the function equals at 1. And this is what's happening as it approaches from the right. D, f is increasing on x is less than -4. So I know as we get closer to -4 that the function is increasing. So I'm going to go ahead and draw an increasing point there, or increasing function. And E, the limit as x approaches -4 from the left, is less than the limit as x approaches -4 from the right. So we don't exactly know what those values are. We just know that from the left, it's less than from the right. So I'm going to say that this is -3. That works. And we don't know if it's open or closed. And then at -4 coming from the right, we know that this has to be greater than coming from the left. So that's why I said I was going to come back to that one. And I'm going to draw that arrow so it keeps going. Again, we don't know if those are open or closed, but we know that's a possible graph that it could be. All right, so that covers all of our graphical limits. Now let's look at some limits analytically or through functions. So just a reminder, when we are looking at the limits analytically, we can substitute the x value in, and that will give us the y value. So in this case, the limit as x approaches -1 means we're going to substitute -1 in for x, which gives us -1 squared plus 2 times -1 minus 4. And when we evaluate that, we get -5. And number 2, same thing. Substitute 2 in for x, and we get 3 times 2 minus 2. And when we evaluate that, we get the square root of 4, which is 2. 3 and 4 are a tiny bit different because in 3, if we substitute in 0 for x, then we get a denominator of 0, which is undefined. That doesn't work. That's a good clue. You have to do something a little bit extra. So we're going to factor something out of this. So I'm going to change this to the limit as x approaches 0 and just rewrite this function as x times 4x minus 5, factor the x out of that. And by doing that, I can then divide x divided by x is 1. So those cancel. And that leaves us with 4 times 0 minus 5, which is negative 5. I got a little messed up. That was 4 times 0. And same thing in number 4. If we substitute negative 7 in, we get negative 7 plus 7 is 0. A denominator of 0 doesn't work. So I'm going to rewrite this function by factoring out the top, the limit as x approaches negative 7. And I have x plus 7 in the denominator, which means my goal is going to be to get an x plus 7 in the numerator also, so that those cancel out. And this function does indeed factor to x plus 7 times 2x minus 1. And now I can divide x plus 7 divided by x plus 7. And that leaves us with 2 times negative 7 minus 1, which is negative 15. Okay, just another couple quick notes. We just have these little trig rules. The limit as x approaches 0 of sine x over x. As a reminder, that is equal to 1. And also the limit as approaches infinity. The limit as x approaches infinity of sine x over x is equal to 0. It's just a couple trig rules for you to remember. All right, and last thing, on to continuity. This is the last thing we've got to do. For f of x to be continuous at x equals c, the following 3 conditions must be met. First, the limit as x approaches a of whatever function has to exist. And remember, in order for it to exist, the limit from the left has to be the same as the limit from the right. Requirement number 2, f of a has to exist. There can't just be a whole, there has to be a value at that function. And third condition, those two values have to be equal to each other. The limit as x approaches a of f of x has to be equal to f of a. And when a function is not continuous, there are 3 types of discontinuities. One type is a removable discontinuity, and that looks like a hole in a function. We could also have an infinite discontinuity. And when we have an infinite discontinuity, that looks like a vertical asymptote. And the last kind is a step or jump discontinuity, which looks like when the limit from the left is not equal to the limit from the right. That gives us a step or a jump discontinuity. All right, so I know that was a lot about limits and continuity. Hopefully that gave you a little bit of a refresher on what we did back in Unit 2. You are always welcome to go back and review those notes if that's helpful as well.